Hello and welcome back to Unbounded Operators, the video series where we extend our standard functional analysis knowledge. And indeed, in today's part 13, we will define so-called self-adjoint and symmetric operators on Hilbert spaces. These are two important notions, and I can already tell you that for unbounded operators, they don't coincide. So in particular, the domains of the corresponding operators will be important. However, as always, before we go into the definition, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And in order to give something back to my supporters, you can find additional material with the link in the description. Okay, then without further ado, let's immediately jump to an operator T acting between two Hilbert spaces x and y. And as you already know, in general such a linear operator is not defined on the whole Hilbert space x, so we have a domain dt. However, usually in the interesting cases, the operator is still densely defined, which means that the closure of the domain is the whole Hilbert space x. And moreover, this dense domain also guarantees that the adjoint of T is well defined. The standard notation of the adjoint is T star, and it goes from the Hilbert space y into x. And indeed, the defining property of the adjoint you already know from linear algebra or from the bounded case, because in the unbounded case it looks really similar. Namely, if we consider our operator T in the inner product of y and we want to push it to the left hand side, then we get our adjoint T star in the inner product of x. However, this identity only makes sense for vectors x from the domain of T and for vectors y from the domain of T star. And now of course what you see here is that we cannot really compare the two domains because they lie in different Hilbert spaces. Such a comparison only works if we have the same Hilbert space on the left hand side and the right hand side. And indeed, this is what we will do in this video. We will consider operators from x into x again. This has the big advantage that we can compare T with T star. Now we can just see T and T star acting in the same direction. In addition, now it's also really easy to form the intersection of both domains. In fact, now it could also happen that the two domains are exactly the same set. And in that case, we can actually define what it means to have a self-adjoint operator. This means that T and T star should actually be the same operator. And we can formulate that by using the inner product relation from before. But now we don't have a space y anymore. Therefore, let's use x and x tilde for the two vectors in the inner product. And now acting T on the right should be the same as acting T on the left. And this equation makes sense whenever x and x tilde lie in the domain of T. However, because of this domain restriction, the property here is not what we can call self-adjoint in the unbounded case. This makes sense because the domain of the adjoint T star could still be larger than the domain of T. Therefore, this nice equation here actually just tells us that T star is an extension of T. So you can see, in general, the two operators are not exactly the same. And therefore, in the unbounded case, we distinguish symmetric operators, which satisfy this equation, and self-adjoint operators, which actually have an equality here. And with that knowledge, we basically already have the next definition here. So we just take one Hilbert space x and an operator T from x to x. And as always, we assume that T is densely defined because otherwise the adjoint does not make sense. And as we have already seen, the definition we want to write down now definitely needs the adjoint of T. And the first notion here is that T is called a symmetric operator. And by definition, this should mean that the inner product is the same no matter if T is on the right or on the left. And in fact, for a densely defined operator, we have the equivalence here. We know that T star is exactly defined in that way, so it just means that T star is an extension of T. So this is what we mean by a symmetric operator. The two operators here act the same way, but one domain could be bigger than the other. So in general, for a symmetric operator, the domain of the adjoint is bigger than the original domain. So the only chance to get equality of the domains is to make the smaller one bigger. In that case, by definition, the domain of the adjoint could get smaller and maybe we reach an equilibrium in the middle. And then we would speak of a self-adjoint operator because there is no difference between t and its adjoint. So we just write t star is equal to t, which also means that the two domains coincide. And one important thing you can already see in this definition, namely, this only works if t is a closed operator already. We already know that t star is always a closed operator, so if we start with a non-closed operator t, it can never be self-adjoint. And this nice observation already leads to the next definition, because often we deal only with closable operators. Then we already know that t has a closure, but we might not know this operator explicitly. And then the term essentially self-adjoint comes in, which just tells us that the closure of t is self-adjoint. Hence the formula here is also simple, you just take t in the closure. And this one has a well-defined adjoint, which is equal to t over line again. So you see, this is exactly the same thing as saying that t over line, the closure of t, is self-adjoint. Okay, so this is the new definition, and please note that for bounded operators t that are defined on the whole Hilbert space X, these notions are all the same. So the distinction we do here is only needed because we consider unbounded operators. And in fact, soon we will see that we often need the strong notion of self-adjointness if we want to prove some important theorems. However, first let's say something about general symmetric operators. Namely, a symmetric operator is necessarily a closable operator. This might not be so surprising, but it also means that we can look at the closure of t as well. And now the nice result we get is that the closure is still a symmetric operator. This is not hard to show at all, so let's quickly write down the proof. As already mentioned and shown in the last videos, t star is always a closed operator. And now by assumption, t star is an extension of t. So you see, t has a closed operator as an extension, which means it's definitely closable. Indeed, this is easy to see because the graph of t lies inside a closed graph as well. And in fact, the closure of t is always the smallest possible extension which is closed. In other words, t star is still an extension of t over line. And now it turns out that the star does not care about the closure at all. This means that t over line star is exactly the same operator. If you don't believe that, we can quickly show that by using our graph properties from part 11. Indeed, part 11 tells us that the graph of the adjoint is always given by an orthogonal complement. The only thing that comes in here is a minus sign and flipping the coordinates with this operator v. And this result we can use now to calculate the graph of t over line star. And by this property, it's simply given by the graph of the closure of minus t. However, by the definition of the closure of an operator, we just have to take the closure of the corresponding graph. So we just have the orthogonal complement of this closure. And there we can use the fact that the orthogonal complement does not care about the closure at all, so we can just omit it altogether. Which immediately gives us the original graph of t star. So the two graphs coincide, which means that the two operators have to coincide as well. And this is already the whole proof. We have shown that the closure of t is also symmetric. So the result we get here is that the notions closable and closed are really important if you want to talk about symmetric and self-adjoint operators. And now in order to make everything more concrete, let's look at a very important example. Namely, I want to talk about the differentiation operator on the Hilbert space L2. This means we consider here big L2, so the square integrable functions defined on R. Or to say it more precisely, the vectors here are equivalence classes of square integrable functions from R to C. And the inner product you should know as an integral. And now I want to define the operator t by using the derivative of differentiable functions in L2. So Tx is just the classical derivative of the function x. And this one we usually denote with a prime. Moreover, now I also want to multiply this result by a scalar. And the scalar is exactly the complex number I. Why we need that you will see soon when we write down the inner product of Tx with another vector. But before we do that, let's first talk about the domain of this operator, because we can definitely not define this operator on the whole space X. The classical derivative has to exist, and an easy choice would be to use C-infinity functions. And we can make it even nicer by saying that all the functions here need to have compact support. So these are really special functions, and we discuss them a lot in my series about distributions. But here you just have to know that we can approximate every L2 function by these nice functions. And this approximation result tells us that our operator T is a densely defined operator. So the adjoint is well defined, and we can go to our inner product. So let's take x and y as C-infinity functions with compact support and write down y with Tx. So by definition, this is just an integral where the first component gets a complex conjugation. So let's just write y of t complex conjugate. And then the second term is t of x, which is simply I times x prime. So not so complicated, and here we just integrate over t. The domain of integration is written as R, but we already know we could also choose a compact set in R to get the same result. And this is actually helpful because it means that integration by parts is possible. And even better, the boundary terms in the integration by parts formula will just vanish. So what remains is just a minus sign and the integral again. But in this integration, the derivative is not at x, but at y. Otherwise, nothing really changes, so the integration by parts formula is really simple here. And now for the last step, you might already guess that we want to push I to the function y prime. And in fact, this step will eat the minus sign because now I is under the complex conjugation. And with that we are done, because we can rewrite this integral as an inner product again. However, now the first component has ty and the second component is just x. And this is exactly what we wanted. We have the equality of the two inner products. And now you already know, the conclusion of that is that t is a symmetric operator. So you can remember, this combination I with the classical derivative gives us an operator which is close to a self-adjoint operator. However, in order to actually make it into a self-adjoint operator, we have to enlarge this domain here much more. And this also includes that one has to leave the classical notion of a derivative and go to a more general one. Of course, this is a discussion we should definitely do in another video. However, in this series we should first talk about the properties of symmetric and self-adjoint operators on Hilbert spaces. So let's do that in the next videos, and I really hope I meet you there. Have a nice day and bye bye.